Okay, hello everyone. I'm very pleased to open the session of PhD Open Lectures and welcome our speaker, our lecturer, who is Leszek Kołodziejczyk. Leszek is a mathematician. He's working in mathematical logic, but somehow on the bridge between mathematical logic and the complexity theory. And he actually contributed results that explain why some complexity problems are difficult to solve. And these results are based on the so-called reverse mathematics and proof theory. And by the way, as you could read in the on the website, Leszek also provided some lower bound on the proof techniques which are needed to prove Fermat last theorem. But today we will be closer to say the complexity and computer science. So Leszek, well, the stage is yours, and welcome as a lecturer of PhD Open.
Thanks a lot, Damian. Thank you for coming, everybody. So I have to say that when I got invited to give these lectures, I was on the one hand honored, on the other a bit terrified, and that's because I really don't think of myself as a computer scientist. I think of myself as a mathematical logician. And moreover, when I reflect on the reasons that got me hooked on logic many, many years ago, somewhere in high school, I guess, things like Gödel's theorem and non-classical logics and various other things, it's clear to me that psychologically, one of the reasons why I like this stuff was some sort of general vague dislike of computers and technology. And these results were telling me that computers won't solve everything and so on. So I'm not a computer scientist in any serious sense of the word, and it was not clear to me what I could talk to you about. In the end, I decided to give a brief introduction over these 3 lectures to an area known as propositional proof complexity, or in computer science logic, proof complexity simply. Because it's an area I've dabbled in. I have like 3 papers in the area co-authored and a few others that are related. And I think it's also an important area, somehow bridging complexity theory and logic, though it's moving in the purely complexity direction ever more rapidly these days. But it still has various interesting connections to logic. And I think it's an important area that doesn't get discussed much in Poland. So I'm hoping that even if these things are kind of basic, you will benefit from them. And I don't plan to do only basic and classical stuff. I don't plan to go over complicated things, but some of these results will be new and kind of interesting, especially the ones tomorrow and on Saturday. Okay, so now how do I move my slides? There it is. Okay, so what is this field about? What is this field of propositional proof complexity or proof complexity about? Well, as you can guess, it's all in the name, right? It's supposed to be the study of how difficult it is to prove formulas of propositional logic, propositional tautologies. If not P implies P, then P, and various other things more fancy than that. In systems, in proof systems for propositional logic. And of course, how difficult should not be understood in, say, a psychological sense or as a sort of measure of creativity, but in the sense of how complex the proof is under some sort of measure of complexity, and we'll get to various specific measures during this course. And the focus is on lower bounds. Upper bounds are also quite often interesting, and they matter. Upper bounds are often a tool to prove lower bounds as well. But I would say the main driving interest has been lower bounds over the years. So let's start with a definition of what a proof system is. This will be a computer scientist's definition. It's not much of a logician's definition. I mean, many more orthodox logicians would balk at this extremely general notion of proof system that I'm proposing here, but it's the universally accepted one in the field since the mid-1970s. So if you let out, yes.
Your voice sounds a bit muffled. Maybe is there something obstructing your microphone or something?
I'm not using a microphone, just the laptop mic.
Could you bring it a bit closer, maybe to you? Or...
Okay, I can try that. I will see how that works with the writing later on, but is that better?
Yes.
Okay, so I'll try to do that, but then every now and then I'll have to move away a little bit to scribble something. Okay, so if we write Tate for the set of all tautological formulas, and let's just agree that we'll use only DNFs because that's sufficient to get completeness of this set of this language, then a propositional proof system is simply a polynomial time computable map from, say, 0-1 strings that code, strings over some other finite alphabet onto the set of tautologies. Okay, so we should, the range of this map should contain only tautologies. So the proof system is sound. It doesn't prove anything that's not a tautology. And it contains all tautologies. That means that the proof system is complete. So it proves everything. Okay, so that's just a definition. If you take a more typical system that you might have studied if you took a logic course at some point, then you interpret that as a system in this sense by mapping a proof in the more traditional sense to the last formula in the proof, if it's a proof of something, and if it's not a proof of something, just map it to P or not P or your favorite tautology. So it's easy to interpret more sane, more traditional systems in this way. Okay, so what I'm planning to do over these lectures is give you a selection of some ideas and some results that have been proved in this area. Some of this will be classical, which means like mostly from 1990 to 2010 or something like that. Some stuff will be new from like 2 years ago or less. This will not be a very comprehensive survey. I can't claim to have a comprehensive understanding and erudition in the entire field. So this is heavily biased by my own preferences, which tilt to, say, more logic than combinatorics. There will be, mainly stuff that relies on some sort of idea in logic. And will focus on things that are not too advanced, either purely technically or conceptually. So I don't want to, discuss any extremely technical argument that would have us doing, combinatorics for this one argument over 2 lectures, for instance. And I don't want to introduce anything that would require discussing a concept that would take a lecture to introduce. So for instance, I won't say anything about connections between proof complexity and so-called axiomatic theories of bounded arithmetic, which I've done a lot of work in. I won't say anything about how switching lemmas, the ones that you might know from parity lower bound and circuit complexity, how they intervene, and other stuff. We won't talk about the use of expanders, although it matters a lot, same for communication complexity in this field. So these things might get mentioned in passing somewhere, but will not be expanded upon. Okay, so this will be hopefully relatively simple, easy to understand stuff. By the way, please do interrupt me if you have a question. Ideally, just turn your mic on and ask the question, because I might not notice if it's on the chat. I'm known for it, not noticing the chat.
Notice you sound better if you move towards the right, I think. This is
the right? This is my right.
Yes.
Okay.
Yeah, so when you're to the left, the audio's bad, but when
Okay, I'll try to twist towards the right and not lose my neck in the process. Okay, so I would also like to say something about the motivation for proof complexity. And there are 2 bits of motivation. One will have to wait a little bit with explaining. The other I can tell you right away. This was the original motivation for studying complexity of propositional proofs. So this definition of a propositional proof system is precisely intended to give the following easy equivalence. If you define a system to be p-bounded, this simply means polynomially bounded. If it has polynomial size proofs of all tautologies, so all tautologies have a small proof in this proof system, then such a polynomially bounded proof system exists if and only if NP equals co-NP. This is just an exercise, okay? We can actually do it, why not? In one direction, I'm assuming that you've seen some complexity theory at some point, so you know that the set of satisfiable CNFs is NP complete. So taut being the dual set, tautological DNFs, that's co-NP complete. So if we had a P-bounded proof system, we could write down an NP definition of this co-NP complete set. Something is a tautology if and only if there exists a polynomially bounded proof that proves this something in our proof system. Okay, so the existence of a polynomially bounded proof system would imply NP equals co-NP. And in the other direction, if NP equals co-NP, so you have a non-deterministic polytime machine that accepts exactly tautologies, then you treat computations of such a machine as proofs, simply. And that's a polynomially bounded proof system in that case. Okay. So the people who came up with this definition, Stephen Cook actually, and then his PhD student at the time, Robert Reckow, they had this idea. It was called Cook's program for approaching the NP versus co-NP problem, or proving that they're distinct. Namely, let's start with the proof systems we know, from a textbook or something. Let's prove, or even weaker ones, let's prove lower bounds in them, super polynomial lower bounds in them, and then on stronger systems, and then on stronger ones, and so on, until eventually we learn in the process that there can be no polynomially bounded proof system, and that'll tell us that NP doesn't equal co-NP. Okay, so that was the original idea. And it's led to a number of interesting results over the years. This was the main driver of the field for a number of decades. But it's fizzled out, I would say, in the sense that there's not much progress right now towards generally proving that there's no polynomially bounded proof system. So you'll see in a while where the borderline is right now between what systems we can prove lower bounds for and what systems we can't, and that's a pretty shamefully low border. So Cook's program, has not fulfilled the hopes that maybe some had put in it, but it's an interesting program that nevertheless, and it has led to a lot of great work. So, but so far that was the original motivation. There's other stuff to motivate the area nowadays. So now, let me say what. Let me give you some examples of proof systems that all fall under this definition. We're not going to check carefully that they do, but they do. So one important class of propositional proof systems is known in the field as Fraga systems, from Gottlob Frege, this early late 19th century, so early modern logician, we could say. And these are basically, if you ever took a logic course, then there's a pretty high likelihood that you were taught some proof system for propositional logic. And then it's very likely that it was a Frege system. So examples of what can be called a Frege system are as follows. So firstly, this is a mainstay of many mathematical logic and I guess computer science logic courses as well. Something called the Hilbert style system. We have a few finitely many axiom schemes, like every formula of the form not F implies F, where F is any formula, that's an axiom, and some other axioms as well, that won't be the only one. And you're going to have rules that tell you what you can derive if you derived some other stuff. A typical example is modus ponens. So if you proved F implies G and you've proved F, then you can derive G. Okay, so this is, I guess that some of you have seen this sort of system. That would count as a Frege system. Another one that I won't discuss in detail, but you might have seen this instead of, or in addition to the kind of Hilbert style thing, is something known as sequent calculus. So in sequent calculus, a line in the proof is, say, gamma arrow delta, where gamma and delta are finite sets of formulas or finite lists of formulas. we might distinguish between the order. Doesn't matter too much. And what this means is that the conjunction of everything in gamma implies the disjunction of everything in delta, and there are appropriate rules for manipulating this. In the sort of sequent calculus that I'm thinking about, an important rule is an analog of modus ponens known as the cut rule. We'll see what cut rule looks in a different system in a moment. Yet another, this is a particularly simple example of something that could count as a Fraga system. This is called a Tate style system. So our official connectives would be only and or as binary connectives. And we also allow negation, but just at variables. So we'll write x bar for negated x. I'm not sure if you're used to the word literal, so maybe I'll write it. We will need it later on. So let me write this. So literal equals variable or negated variable. So formulas in the system are just ands and ors of literals. Beyond the variables, you define negation by the De Morgan laws, and the axioms are, just very. I mean, the rules are very obvious. I mean, you can write x or not x or whatever. That's an axiom. You don't need anything to know anything before that. If you know that a line is interpreted as a disjunction with the formulas here. If you know something, then you know that something or f as well. That's a weak winning rule. If you know that something and a disjunct, you may replace the disjunct by the disjunction. So there are two symmetric rules for introducing a disjunction. There is a rule for introducing conjunction. If you know that gamma or f, and you know that gamma or g, then you know that gamma or the conjunction of f and g. And you also have cut. So cut says that if you know that gamma or f, and you also know gamma or not f, this means f implies gamma, then you can derive gamma. So this is a very simple proof system. And that's also like at the same level of strength as the ones I've discussed until now. So now how do I move between the slides? I have to turn off annotation or something. I don't know. Okay. So it used to be that only this first kind of system, this one with a finite list of axioms and modus ponens, was called the Fraga system. I think actually somebody got confused between what Hilbert did and what Fraga did, and this was like a misnomer. But it turns out that all of these systems I mentioned until now, they're actually equivalent in an important sense. So any two of the ones that I've discussed, they're pairwise equivalent with a respective relation known as P simulation, which is simply a polynomial time computable translation. So if you can prove a formula in one of these systems, then there's a translation into another one that's polynomial time computable. In particular, the proof only grows polynomially in size. So these systems, from the point of view of complexity, they're all the same. At least if you're okay with polynomial growth. Okay, so these things are all at the same level. So here's something that's different. I mean, it's not provably different. We can't prove it, but this is something that we believe should be stronger than those guys. Namely, if you allow an additional rule that lets you take a fresh variable, let's say x, that hasn't appeared in the proof until now, and say that a given formula f that doesn't contain x is equivalent to x. So if you're allowed to use single variables as abbreviations for formulas, and you add that to any of these previous systems, of course, if you don't have equivalence as an official connective, you can simulate it using conjunction and negation. So if you do something like this, you get something that's known as an extended Fraga system. And more or less, since you can shorten long formulas by using these variables, the size of a proof, size means just number of symbols, right? I mean, So the size of a proof on extended Frege is more or less up to a square factor or something, the number of steps you need to prove a formula in a more typical in a textbook system. So we believe, it is believed that these things are stronger. I mean that there are formulas that require, for instance, few steps to prove, but the steps have to be long if you're not allowed to abbreviate formulas. So people tend to believe that this is properly stronger in terms of P simulation than Frege systems. And now let's go in the opposite direction, okay? So if you take a Frege system and restrict it to formulas of some bounded depth, where by depth, I mean, think about these formulas just constructed of from ands, ors, and negations at the bottom. So the depth is how many times you have to alternate between and or in the syntactic tree. So for instance, a variable or negated variable, that's depth 0. A conjunction of variables and negated variables, that's depth 1. And a CNF or a DNF, that's depth 2, because it's an and of ors of literals or an or of ands, okay? So if you fix a constant G and say that you're proving things just like you did previously using the same rules, but you're only allowed to use formulas of depth like D, 10 for instance, or whatever your favorite number is, then that's called a depth D system. And if you take the family of these systems for all D, that's known as the family of bounded depth or bounded depth Frege systems. And each of these guys is known to be strictly weaker than a Frege system in the sense of P simulation. So there are formulas. I'll mention one. We won't be able to prove this separation, but I'll mention one that have short proofs in a typical textbook style system, but can't be proved shortly, need exponentially long proofs in bounded depth. So these guys are strictly weaker, and they're at the level where you can actually prove separations. Now, I want to go even lower than that, down to a proof system that's known as a resolution. So this is something that was, well, it's designed as a refutation system. So you disprove, in other words, refute. Refute means the same thing as disprove, basically. You disprove unsatisfiable CNFs instead of proving tautological DNFs. So you take a CNF and you disprove it. And the way you do it is you represent, well, what's a CNF? A CNF is a conjunction of ors of literals. Now we call an or of literals a clause. Well, we normally write it as just a list of literals, and we think of it as implicitly as a disjunction. And if we state a number of these clauses, like a set, 3 clauses, for instance, so we think of that as a conjunction of them. So a CNF is a set of clauses where a clause is a disjunction of literals. And now, given such a set of clauses, if it's unsatisfiable, you can actually start manipulating it using only the following rule. If you've got a clause C or X, where X is a variable, and you've got another clause D or not X, then you can derive C or D. Okay, so this is, if you think of these as sets or lists, you just take the union of C and D. You might also sometimes allow the weakening rule. So just to remind you what weakening is, maybe I won't go back to the previous slide, but weakening is just take C and derive C plus something else. So you can always add new formulas to a disjunction without making it false, if it was true until this point. And eventually, if the formula is unsatisfiable, you will be able to derive the empty clause, which is an empty disjunction. Empty disjunctions are the constant false, they're unsatisfiable. So that proves that the formula had to be unsatisfiable. So that's how resolution works. If you compare it to these Frege systems, you can think of it as a depth 0 system. So the only thing that appears in a line is a variable or is a negated variable, but the line in fact is a disjunction of such things. Okay.
Sorry, I'm a bit confused.
Yes.
Comma a comma corresponds to a...
Yeah, a comma corresponds to a union, which you think of as an or, okay?
Comma,
So it's a list of literals. So C is a bunch of literals itself, and we also have X here. So this is interpreted as the disjunction of everything in C or X.
okay.
And yeah, maybe let's discuss why this is a correct rule, why it's a sound rule. Okay, so we know that either something in C holds or X does, and we also know that either something in D holds or not X does. And since it cannot be the case that both X makes this true and not X makes that true, that means that either something in C must hold or something in D must hold. So that's why you can derive this. I'll have an example in a while. Maybe the next slide is an example. Yeah. So here's an example of a resolution proof. This is the official way how you could present it, as like a list of formulas. But you should really think of such proofs as DAGs, as directed acyclic graphs, as in the picture on the right. Okay. So let's try to refute the following unsatisfiable CNF: X or Y, and X or not Y, and not X or Z, and not X or not Z or W, and not Z or not W. It's not a particularly reasonable or interesting formula. It's just, it was complicated enough to fit on this slide, or simple enough to fit on the slide, sorry, but complicated enough so that I could write a proof with one interesting property that I'll get to in a moment. So from X and Y and X and not Y, X or Y and X or not Y, the clauses of the formula are marked in red. They're called initial clauses. You can derive X by resolution. Okay, so this is a typical instance of the resolution. And from X and the initial clause not X or not Z or W, you can derive not Z or W. Okay. You also have a clause in your formula that says not Z or not W. So from this and the one that we have here, not Z or W, you can derive not Z. And on the other hand, from this X here and the clause not X or Z in our formula, we can derive Z. So now we have Z and we have not Z. We resolve them. We use the resolution rule on them, and we get the empty clause. Okay, so if you've derived Z and not Z, you get a contradiction direct. Okay, so this is a resolution refutation. There is one interesting thing about this particular resolution refutation, namely this derived clause X. So this is not a clause of the original formula, it's a derived clause, is used as a premise, meaning it's used, you know, as one of the things we need to derive a formula and a rule 2 times. To derive clause Z, which is number 5, we use line 3, which is X. And then again, to derive not Z or W, which is line 7, we use X again, that's 3, right? So this corresponds to the proof, this graph of the proof being a DAG. It's not a tree. You have a guy here that's it's not a tree-like DAG. You have a guy here from which 2 arrows exit. It has fan out greater than 1. So this is something that we call a DAG-like resolution proof. This is perfectly allowed in resolution, but you might want to consider a weaker proof system where you don't want to allow such things. Okay, so this guy here in this proof, that's the same proof from the previous page, makes it a non-tree-like proof. We could consider a proof system that's known as tree-like resolution, where we don't allow that. So if you want to use the same thing twice in 2 different inferences and in 2 different reasoning steps, and it's not a part of your original formula, so it's not one of these initial clauses marked in red, then you have to derive it 2 times, right? So that would correspond to turning this graph into something like this. It's the same graph, except that I copied the other derivation of X and the use of X here. Okay, so this is now a tree, and as you can see, it grew in size. It's a bigger graph. It has more nodes than previously. And in general, tree-like resolution, I think this is something we'll do during class at some point, maybe even today. Tree-like resolution is strictly weaker than resolution, full resolution that allows DAG-like proofs. Okay, so this is This is a different proof system. Okay, to complete my gallery of, now I can tell you about another source of motivation for the area that's become possibly the leading motivation, at least for people who do proof complexity of a certain kind. That's a very important part of proof complexity these days. And that's as a tool to get some sort of theoretical understanding of SAT solvers. I don't know, well, you're computer scientists, so I would guess that you may have heard what a SAT solver is. Basically, it's an algorithm for solving SAT. So it's an algorithm that takes a formula and tries to decide whether it's satisfiable or not, or whether it's tautological or not. These are, of course, equivalent problems. So these SAT solvers these days, SAT is theoretically NP complete. So we expect it to be exponential in the worst case, and there are even hypotheses in complexity theory, like the exponential time hypothesis and stronger variants of it, that say that SAT is exponentially hard in the worst case, in a strong sense. But in practice, there are these SAT solvers that routinely deal with very large instances of SAT coming from, say, hardware verification or something like that. Don't ask me about the details. I don't know this stuff, of course. And they deal with them very well most of the time. So SAT is hard in theory and most of the time easy in practice. And these days, SAT solvers get used to more fancy things than just hardware verification. For instance, this is the cover of the August 2017 issue of Communications of the ACM, which discusses a pretty amazing thing. So three guys, among them Viktor Marek, who was an old logician who was educated in Warsaw and then was here in the 60s and 70s. They essentially solved the problem in Ramsey theories, the so-called Boolean Pythagorean triple theorem, using a SAT solver. So the problem asks whether you can color the natural numbers in two colors so that there is no Pythagorean triple. Pythagorean triple means the three numbers that can be the length of the lengths of the sides of a right-angled triangle, like 3, 4, and 5, because 3 squared plus 4 squared equals 5 squared. So the question is whether you can color the natural numbers into two colors so that no Pythagorean triple gets, all three elements get the same color. And the answer is no, because if you color numbers from 1 to 7,825, then you will get a Pythagorean triple that gets the same color. That's a monochromatic triple. And the way they proved this was essentially, very sneakily encoding this as a propositional formula and running a SAT solver. It requires all sorts of pre-processing and optimization and so on, but this is the kind of thing that would have stumped mathematicians possibly forever, but can be done using these guys. So these SAT solvers are pretty important. And the thing is, they're based on resolution most of the time. Certainly the ones that were used to solve this problem are. So inside most of these even state-of-the-art SAT solvers, there's a small core called DPLL for Davis, Putnam, Logel, and Loveman from the 60s. And it's the following procedure. I mean, don't judge my pseudocode, my attempted pseudocode too harshly. I'll try to explain what this says. So it's the following procedure that takes a formula, takes a partial assignment. The formula is F, the partial assignment is rho. So some variables are set in rho, some aren't. And it tries to determine whether there is a satisfying assignment for F that extends rho, okay? What it does is the following. It first checks whether maybe rho already satisfies F. So maybe in each clause of F, clause is a disjunction, there is a literal that's true under rho. In that case, you output rho as your satisfying assignment and you terminate, you do nothing else. If that doesn't happen, then check if row doesn't falsify. The word clause is missing here. So maybe there's one clause in F such that row already falsifies each literal in it. In that case, we know that row will always falsify F, and we can't extend row to satisfy it, so we can simply return false. And in case neither of these happens, so row doesn't satisfy F yet, but we haven't ruled out satisfying F for now. We haven't ruled out satisfying F for now. We have to choose some literal that's not yet set in row. How you choose that will depend on the specific implementation of DPLL and what heuristics it uses. This is a very complicated problem. How to choose that? This literal is called the decision literal, and then you first run the same procedure on F extended by and row extended by setting the literal to say 0, and then if that doesn't return a satisfying assignment, try the same thing with row, but with X set to 1. And if neither of these works, then you can return false. There's no satisfying assignment for F that extends row. Okay. So the interesting thing about this, or the connection to proof complexity, is that this is very closely connected to tree-like resolution. So if you somehow write down the graph of what such a procedure does when run on F and starting with the empty assignment, then that essentially produces a tree-like resolution proof of or refutation of F if F is unsatisfiable. I mean, it's not really interesting what this does on satisfiable formulas, but if F is unsatisfiable, then a run on of this procedure on F is essentially a tree-like resolution refutation of F. And on the other hand, if you have a tree-like resolution refutation, if you have a version of DPLL which makes the right guesses concerning which decision literal to choose, then it can essentially do a depth-first search of the refutation, and then it will eventually return false if it was really a refutation. So loosely speaking, tree-like resolution corresponds to non-deterministic DPLL in the sense that in resolution we're allowed to choose the decision literals however we want to, and in DPLL it's presumably deterministic or at best randomized, and it will not have complete freedom to guess what literal to choose. Maybe it's worth going back to this picture. So what run of DPLL does on this formula that we're refuting here does this particular refutation correspond to? Well, starting with the empty assignment, the DPLL prover, it takes Z as its decision literal. And first, it assumes that Z is falsified. So the assignment that the DPLL, the run of DPLL has is the negation of the clause at hand. So it for now it extends the assignment by setting Z to false, and then it makes X the decision literal. And if Z is false and X is false, our refutation doesn't actually care about Z anymore, but the DPLL remembers that Z is false as well. Then if you consider what possible options there are for setting Y, you will eventually falsify one of the clauses of our formula. Either you will learn that not X and not Y, or that X and not Y. So X cannot be false. Let's go back to here. Here we just know that Z is false. Let's assume that X is true. Well, then X is true and Z is false, but this also contradicts one of the clauses of our formula. So that's impossible. Okay, and so on. So this is the sort of connection between DPLL and tree-like resolution. So in particular, strong lower bounds on the size of a tree resolution proof that you need to refute a certain formula, they will tell you that any DPLL-based solver will require a long time to figure out this formula, to learn that it's unsatisfiable. Modern SAT solvers, well, the typical thing is something called a CDCL SAT solver. That's conflict-driven clause learning. they do much more stuff than DPLL does, but they're still based on a similar thing. So they have some additional stuff inside. The most important things are close learning and restarts. So firstly, whenever the prover reaches a contradiction, so discovers that some assignment can't work because it falsifies a clause of the formula, it learns a clause. It has some heuristics for figuring out which clause to learn. It learns a clause that is an easy consequence of the original formula, provable in resolution, and it adds it to the clauses of the formula. So if we were trying to find a satisfying assignment for F, and we have this easy consequence of F, namely C, then we can add C to the clauses of F as a new conjunct. And we consider, from now on, we run with F extended by the new clause C. So that's close learning. Another thing is which is supposedly very important in practice for, I think, pretty mysterious reasons. Every now and then the solver decides to just scrap completely the current assignment, the current partial assignment row, go back to the empty set, but just keep the clauses it has learned, and basically restart from scratch, but with the new learned clauses added to F. And all these things make the proof that corresponds to a run of the solver no longer tree-like, because in some sense these learned clauses are like lemmas, and lemmas are a tree-like proof of lemmas corresponds to a DAG-like proof. That's a very kind of high-level reason why this happens, but it's still modeled by resolution. And if you make this model non-deterministic enough, it's exactly resolution. So if you have a CDCL SAT solver that makes exactly the right guesses miraculously, and miraculously tells when to restart, then it can essentially learn the clauses in any given resolution refutation. So this connection between tree-like resolution and DPLL gets extended to a connection between full resolution and CDCL. In other words, a resolution lower bound tells you that typical SAT solvers are going to run crazy long on the given formula. Okay, so that's why people care about this. And that's why we will spend a lot of time on resolution during this course. Okay, this will be our main proof system. Well, I wanted to add something else to this gallery, to this rogue gallery of proof systems, so that you could see something different that's not so logic-based as the other ones. So here's a proof system called polynomial calculus. So let's fix some field. Formally, for this to be a proof system, it should be some sort of field where you can write down the elements in some effective way. So ideally, a finite field, just think of the two-element field for concreteness, if you need something. And the lines in this proof system are going to be polynomials over this field. So, you know, x squared plus y times z, or something like that. And a line means that the polynomial equals 0. On the supposed variables, it means this polynomial is supposed to evaluate to 0. So that lets us express clauses as polynomials. So the clause x or not y or not z is true exactly if this polynomial is equal to 0, 1 minus x times y times z. Okay, and the rules are simple. Firstly, we want the variables to be Boolean, so we can always assume it's an axiom that x squared minus x equals 0. We can add to polynomials. So if we know that p is 0 and q is 0, then we can also know that ap plus bq equals 0, or a and b are elements of the field. And whenever we know that p equals 0, then if we multiply it by any variable, it still is 0. Okay, and typically we write out, to measure the size, we write out polynomials as sums of monomials. That's the usual way of studying the size in this sort of system. And the refutation, so a proof that a formula or a set of polynomials doesn't have to come from a formula, is unsatisfiable, is a derivation of the constant 1. Because this certainly doesn't equal 0. So if you derive 1 equals 0 from your system of polynomials, that's a contradiction. Okay, so that means that your set of polynomials couldn't have been satisfied in the first place. Okay, So as I said, typically you assume there have to be a finite field or maybe Q or something like that, but actually most lower bounds for the system work for any field. And often you want this proof system to simulate resolution. So there's one stupid problem in that if you take a clause consisting of many positive variables, X or Y or Z or something else, then that would translate into the polynomial 1 minus X times 1 minus Y times 1 minus Z and so on. If you write that out as a sum of monomials, that's exponentially many monomials. You don't want that. You don't want it to be exponential for such a stupid reason. So there is a trick, which is to add additional variables for these negated propositional variables, say X bar, and have these, they're called complementarity axioms, 1 minus X bar. And that lets you use X bar instead of 1 minus X, basically. And that's called PCR, or polynomial calculus with resolutions. It's what polynomial calculus should have been defined as, frankly, originally. Okay, so I think that's enough in terms of giving a general discussion. There are many different proof systems that people have studied. For instance, you could take any axiomatic theory, like Zermelo-Frankel set theory or whatever you like, and consider a proof of this thing as a tautology in the theory as a proof in your proof system. So any reasonable axiomatic theory counts as a propositional proof system. There are these say integer linear programming based systems where they work with, their lines are linear inequalities with integer coefficients. Such a thing is called cutting planes. There are all sorts of so-called semi-algebraic systems where lines are polynomial inequalities, but we won't get into that. So to give you an idea of what the landscape is like, so for what sorts of systems there are good lower bounds on proof size. This is pretty terrible. So it's been known for a long time that tree-like resolution requires long proofs of some things. And it's been known since the mid-1980s that resolution does. So exponential lower bounds for resolution have been known from the mid-1980s. We're going to prove one today, not the original one, but one that I think is kind of simple. And you can go a bit higher. There is a pretty sophisticated, but also pretty old by now, very early 1990s result that bounded depth Frege. So, a normal proof system, but you're only allowed to use depth 17 or depth 700 formulas. That's also not going to be polynomially bounded. That's going to require exponentially long proofs for some formulas. And this polynomial calculus, actually over any field, but just for concreteness over the two-element field. So with something like a parity connective, basically. This is also known to be not polynomially bounded. But if you take this very, very lame proof system, whose lines are like in resolution, so they're disjunctions, but a disjunct doesn't have to be just a variable or a negated variable, but any linear equality over the two-element field. So, x plus y plus z equals w plus not z or something like that. So amazingly, a system that operates with disjunctions of such linear equalities over F2, nobody has proved that this doesn't prove all tautologies in polynomial size. That's like, I would say this is like the research frontier these days. So people recently proved that if you have the rationals here instead of F2, then there is an exponential, I think, lower bound. And beyond that, if you take these bounded depth proofs, but you allow yourself an unbounded parity connective, the sum of these x1 through xn is odd. That's already too hard. That's even stronger than this system. And if you go upwards to these textbook systems and even further extensions, that's like completely hopeless. It seems like totally beyond what people can do. Okay. So that was an overview. Here are the things I would like to do during the remaining 2 and not quite half of a lecture. So today, I would like to prove a resolution lower bound, prove some lower bound, exponential lower bound on the proof size of a tautology for resolution, just so that I can introduce some techniques and you can see how this can be done. Because for tree-like resolution, it's really almost trivial. For resolution, there is no fully trivial proof. So we'll do something that's hopefully not too complicated. just to get you in the thick of things. And then tomorrow, I'm hoping to discuss a very important topic called automatability. So which proof systems are automatable and which aren't. And if we manage to do that satisfactorily tomorrow, then on Saturday, we'll discuss a different measure of proof complexity known as space and how it relates to more typical measures. So that's my plan for these 3 days. And today we're going to prove a resolution lower bound. If we don't fit it in the lecture completely, we'll move the rest to class, and I'll leave the technical details to you to work out in class. But I think we'll be able to give an overview during the rest of the lecture. Okay, so let's introduce an auxiliary, a possibly simpler proof complexity measure. We'll call it the width of a proof. Okay. So the width of a clause is simply how many literals it has. So it's a clause consisting of 3 literals, meaning a disjunction of 3 things. Then it has width 3, for instance. And the width of a refutation in resolution is, well, how large the widest clause in the refutation is. So, for instance, in this example that we've been discussing, this has width 3 because this initial clause here already has width 3. All the other clauses are in fact width 2. So if we could somehow derive a contradiction without using this clause, then we would have a width 2 refutation, but we don't.
So they can grow, right? The size of the clauses in the refutation.
Yeah, so this is maybe not a very ideal example. So if we took, for instance, if we had, I don't know, let's have another variable here. If we had v or x or y, and we resolved it with not x or not z or w on the variable x, then we would get v or y or not z or w. So that would be a width 4.
Okay, yeah, I understand. Thank you.
Very good question. Thanks. So the width definitely, that's a typical thing. You will see in a while that we will have non-wide, so narrow, reasonably narrow CNFs, meaning like logarithmic width in the number of variables that require large width to refute resolution. That will be useful for us later. Okay, so that's width. And now the width of refuting f in resolution, or width needed to refute, we'll denote it as w with index r for resolution of a formula f. It would be more proper to write WR of f implies contradiction or something like that to indicate that it's a width of a refutation, but we'll use this simplified notation. So that's the smallest width of a refutation of f in resolution. Okay, so that's how much width in a refutation you need at the least to refute the formula. Okay, so if you have, if this width is 10 and your formula, which is perhaps a 3 CNFs, if it has refutation width 10, then there will be no refutation of width 9. And one of the reasons we're introducing this notion is that proving lower bounds on it can be easy. Not in all cases, but there's a well understood technique, a well understood combinatorial characterization of how you prove lower bounds on width. So let me introduce a game. If you've ever done Ehrenfeucht-Freisse games, or in particular Pebble games, then this will be extremely familiar. It's the sort of thing that people in finite model theory do, for instance. And it was introduced by Albert Atzerias and Victor Dalmau. Atzerias is a guy who does both finite model theory and proof complexity, and he's known for bringing ideas from one field to the other. So the game is determined by a CNF formula that we think of as unsatisfiable, and the number of pebbles in the game. So the formula is f, the number of pebbles is k. There are going to be 2 players. One of them we'll call prover, the other is duplicator. Duplicator claims that he has a satisfying assignment for f. And prover is allowed to ask him about the satisfying assignment in the hope of finding concrete prediction. So in the hope of discovering that this is not really a satisfying assignment. Okay. In the interesting cases, the formula is not satisfiable, so duplicator's claim is false, and duplicator has to basically cheat and lie his way through the game. So the game consists of a number of rounds, potentially infinitely many, and the rounds work like this. So prover has access to these k pebbles, and he takes one of them and places it on a variable. Perhaps some others are already placed on some other variables, and asks what's the value of this variable. And duplicator has to answer with a value, 0 or 1. Okay, and if at any point this assignment on the pebbled variables, that's at most k carry variables, if it falsifies one of the clauses of f, then spoiler wins. And if that never happens, then duplicator wins. So duplicator's aim is to prevent spoiler from catching him in a lie. So here's an example of the game. We'll play with the following 2CNF, which basically says the 3 variables x, y, and z have mutually distinct truth values. Or something like that, or something like that. No, x has the same value as z, and y also has the same value as z, but x has a different value from y. So this is like obviously unsatisfiable. Yeah, so x has a different value from y. We say this as x or y and not x. Sorry, there is some yeah, this should be an or, right? So x or y, this means not x implies y, and this should be an or here. This means x implies not y. So, and so on, right? This formula exactly expresses this property. So x has a different value from y, and they both have the same value as z. So it's obviously unsatisfiable. All the clauses have just 2 literals. So potentially you could try to prove, we could try to find out that it can be satisfied by just using 2 pebbles, but that would work. So assume that prover asks, what's the value of x? I still haven't figured out how exactly I should, okay. So what's the value of x? And duplicator says, for instance, 1. So then the natural question to ask is, what's the value of y? And clearly duplicator has to answer 0 because x has to be different from y. Okay, to satisfy these first 2 clauses of the formula, you need x to have a different value from y. So now spoiler wants to ask, or prover, that's the usual terminology here, prover wants to ask, what's the value of z? And he's expecting to catch duplicator in a contradiction because z should be equivalent to both x and y. But the problem is he cannot ask the value of z without picking up one of the 2 pebbles that he has. He has just 2 pebbles. So for instance, to ask about z, he has to forget about x. So he asks, well, what is z? And duplicator will of course answer 0 because it's equivalent to y. And well, prover then tries to go back to x, but he has to forget about one of the others. So he doesn't catch duplicator in the contradiction either, right? So and this goes on and on. It's clear that duplicator wins this game, I guess. If we know that z is 0 and duplicator is asked about x, he will of course respond 0 and so on. Okay. So this is a game in which duplicator has a winning strategy. I should erase this. I should erase this thing. So here's the characterization that Series and Dalmau came up with. If you've got a KCNF and consider a width, well, this theorem is very difficult with various +1s and strict versus non-strict inequalities, and they took a clever way out in their paper. They simply ignored this assumption here about the connection between width and k. This assumption is missing from the theorem as stated in the paper. They think it's correct as stated here. So if you take a width w that's strictly greater than the width of the formula itself, so f is a k, c, and f, and we take w that's at least k plus 1, then if you want to prove that duplicator, if you want to prove that you need width at least w to refute f in resolution, it's enough to come up with a winning strategy for duplicator in the w pebble game on this formula. And actually, it's an if and only if. If you come up with with such a strategy, then the formula cannot be refuted in width smaller than w in resolution. I wanted to go over one direction of this right now, and then we'll maybe discuss the other one in class if as needed. So let's just prove the one that matters to me right now. So you can think of as a resolution refutation as essentially a prover strategy. So the strategy is the same strategy that essentially the SAT solver used given a refutation, and we looked at when understanding the connection between SAT solving and resolution refutation. So given a refutation P is a pi of the formula F, prover starts at the empty clause, which is unsatisfiable, and tries to maintain as an assignment on the variables of C that they have reached during the game. That's the clause in the refutation they have reached. And his aim is to make sure that the assignment they agreed upon falsifies C. So maybe let me go back to the refutation here. So prover's argument would be, strategy here would be, what is the value of Z? And if duplicator said Z is false, we go here. If duplicator says Z is true, go here. For instance, we ended up here. Then the question becomes, what's the value of W? And if we're told that W is false, so Z is true and W is false, we go here. Okay, so spoiler always maintains this invariant that they have reached a certain clause in the refutation, and the assignment that duplicator has given falsifies this clause. Eventually, you will have to reach an initial clause, so a clause of the CNF, and it will be falsified by the assignment. So prover will win then. And the point is that if the refutation has width W minus 1, then this strategy uses up to W pebbles, so one more than the width of the clauses. The reason that you need this extra pebble is for the resolution variable. So if you're looking at a clause that has 7 variables, say, and it was derived by resolution on a variable x, then you must also ask about the value of x. And before you know what that value is, you must still remember all the variables from the previous clause. So you need 8 cells in memory instead of just, or 8 pebbles instead of just 7. Okay. So if there is a width 7 refutation, then there is a 8 pebble strategy, winning strategy for prover. So if duplicator wins 8 pebble games on this particular formula, then you need at least width 8 to refute it. Okay. The other direction, maybe we'll do it in class, or maybe not. It's less important to me, actually. I don't think we'll need it for any sort of lower bounds. So duplicator winning strategies mean width lower bounds. Okay. And this lets us to look at what is possibly, this lets us look at what is possibly the most famous CNF in proof complexity, namely the Pigeonhole Principle. Okay. So the Pigeonhole Principle for M pigeons and N holes, in Polish zasada szufladkowa, just in case you don't know, but this is the English translation of zasada szufladkowa. Okay. So the Pigeonhole Principle for M and N basically says it's an unsatisfiable CNF as long as M is greater than N. it says that there's an injective multifunction that goes from m pigeons into n holes. Okay? So the variables for PHP are xij, where I index is an index of a pigeon, so it's from 1 to m, and j index is a hole, so it's from 1 to n. Okay, and the idea is that xij is true if in the supposed injection, pigeon number I goes to hole number j. And the clauses are simply this. Firstly, each pigeon goes to a hole. So for every index of a pigeon, we say that it goes to hole number 1 or hole number 2 and so on, or hole number n. And secondly, two pigeons don't go both to the same hole. So we've got two different pigeons, I and I prime, and the hole number j. Then you say that either pigeon I doesn't go to hole j or pigeon I prime doesn't go to hole j. So this is clearly unsatisfiable, clearly in a, say, natural or common sense, or some mathematics, but it turns out you need some non-trivial proof machinery to be able to count well enough to prove this. So this is definitely an unsatisfiable formula, but it's hard to prove in weak enough proof systems. And we would like to start by proving a linear and n width lower bound for refutations of this. The only problem is this sort of thing that we discussed when discussing that example of a width-free refutation. Namely, there's absolutely no point in proving that a refutation of this requires width, I don't know, n or n½ or whatever, because that's clear from the very beginning, because these pigeonhole clauses, a pigeon goes somewhere. They must contain their width n already, so they have to be used in a refutation, because without them the formula is perfectly satisfiable. But they themselves have width n, so it's totally obvious that any proof will require width n. So the width lower bound we could get for trivial reasons, and it would be not very helpful. So we want to reformulate the pigeonhole principle in a more narrow fashion. So the clauses of the CNF will become shorter, but in such a way that we still keep a width lower bound. Okay, so there are a number of options how to do that. One is that you can only keep some of the variables. So keep the variables as saying pigeon I goes to hole j, but don't use a variable x for each I and j, but just take a graph with good enough, a bipartite graph with good enough connectivity properties, an expander graph on the disjoint union of the pigeons and the holes, and only allow a pigeon to go to one of those holes, which is its neighbor in this graph. And the graph has good enough properties, connectivity properties, that it's still going to be hard to disprove. It's going to be even more satisfiable because we've disallowed some combinations of pigeon and hole. Therefore, decreasing the number of variables and shortening the clauses, we can make them constant width if the graph is constant degree, but it's still going to be difficult to prove if we do that right. Another option is to introduce some new variables and basically replace each such long disjunction by a conjunction of shorter disjunction involving these new variables. A third one, which I have my reasons for preferring here, in particular the number of variables, and it will be small. That's my main use of that, and the width lower bound will be complicated. So option number 2 introduces too many variables. Option number 1 would lead us to expanders, and I don't want to talk about them. So we'll do number 3. So instead of having a separate variable for each pigeon and each hole, we will specify the hole to which a given pigeon goes by listing its bits. So we will just specify it as a number in binary notation. Okay, so here's bitwise pigeonhole principle. The variables are xij, where I is still the index of a pigeon, so it's 1 through m, and j is now just from 1 to log n, I guess, I guess the ceiling of log n for this to be correct. And the idea is that xij is 1. Sorry, xi1 is 1 if the first bit of the number of the hole that pigeon I goes to is 1. And if this is 0, then the first bit of the number of the hole that the pigeon goes to is also 0. Okay, so you specify the number of the hole to which pigeon I goes by assigning values to these logarithmically many variables. There are log n many variables, so there are n possible assignments corresponding to each possible hole. Okay, so this is like by definition, it's implicit in the construction itself that there's exactly one hole to which a pigeon can go. And now there is only one sort of clause. Each clause will have logarithmic width. It will be like 2 log n. And for a pair of pigeons, I and I prime, we want to say that they don't go both to the same hole with a certain list of bits. So for instance, if the first bit of the whole number here is 1, then we want to include among our disjunction, among our options why it's not the case that both of these pigeons, I and I prime, go to the same hole. We could say that, well, maybe xi1 fails. Maybe this is false. So that would mean that the whole number to which pigeon I goes begins with 0. Or maybe the same thing happens for xi prime. So xy prime, so if b1 is 1, sorry, if 1 minus b1 is 1, then b1 is 0. So this is negated xy prime 1. So this means the whole number to which pigeon I prime goes for b1 equal to 0 it begins with a 0. The first bit is 0, and so on. Okay, I hope you get it. If not, please ask, because this is not supposed to be a complicated thing. This is the way that we say that the two pigeons I and I prime don't both go to the same hole, and we have to express this separately for each hole. Additionally, if maybe n is not a power of 2, then we have to disallow some holes completely. We say that no pigeon goes to them. Well, that's a very similar looking clause, which just has log n instead of 2 log n literals in it. Okay, so that's how this formula works. And now notice that the clauses in this thing are logarithmic width. So now it's a meaningful result that that you need width n to refute such a bitwise principle. Well, of course, if m is smaller than n, then it's actually satisfiable, so you can't refute it at all. But if m is strictly greater than n, then you can refute it, but you you will need at least width n, or maybe it's n minus 1. But I think it's n. So how do we prove that? Well, we use the game, of course. We use the game. Well, so how do we use it? Duplicator has to win the n pebble game to prove this width lower bound of n variables, with lower bound of n for the width of a refutation. And the duplicator strategy is very simple. So if there are n pebbles, if there are, say, k pebbles on the board, and they correspond to variables, they are on variables corresponding to the following pigeons, I1 up to ik. So we only care about the pigeon numbers, not the whole numbers. Then duplicator maintains an injection from the set of these pigeons, which is at most size n. So actually there is an injection from this set into the set of holes, and answers the questions about specific bits accordingly. So for instance, if n is, I don't know, 100, and pigeon 1 goes to hole 7, so the first bit of 7 is going to be 0 because it's below 50, or below whatever it should be, 64, whatever it is. Then x1 1 will be 0. and so on. Okay. If the whole number to which pigeon 1 goes under this assignment is odd, then the last bit will be 1, x1, I1, and log n here will be 1, and so on. So the only point is that in this way, prover has no chance of catching duplication and contradiction, because the assignment to these variables comes from an actual injection from the pebbled pigeons into the set of holes, which is at least as large as the set of pebbled pigeons. Okay, so that's a proof. That's a proof. I wanted to point out a thing that will be useful for us in a moment. Namely, this proof actually shows more. Namely, a refutation of this bitwise pigeonhole principle not only has to involve a clause that has at least n variables, but it actually has to involve a clause that mentions n different pigeons. So it has to mention, well, n or more variables, but there have to be at least n distinct first indices here. Because if prover is allowed to mention or to pebble more variables than n, as long as he only puts pebbles on variables corresponding to at most n-1 or n pigeons, n pigeons, then the duplicator can still win. Okay, that's I think clear from this proof, hopefully.
So Leszek, this remark also applies to the basic PHP, right? Without bit. Is that true?
Yes, it does. Yes, it does. Yeah, that's a good point. So this remark applies to the basic PHP. Yeah, so if we just wanted to do a size lower bound on some formula, I could use basic PHP and not do this detour from width through width, although the width detour is worth doing anyway, just for introducing this notion of width. So I wanted to have, the next slide will mention something I won't have time to develop, but I think it's also worth knowing. And that mentions, well, width proper. But you're right, we could have played a kind of twisted duplicator prover game from the outset on the original PHP, and that would be enough to get my size lower bound in the end. Okay? So yeah, does this have anything to do with refutation size? And the answer is, surprisingly or not, I don't know, in fact it does. So there is a somewhat deep result, it's not extremely deep, that actually gives size lower bounds directly in terms of width lower bounds. We won't use this directly because we won't have time to prove it. It's not extremely complicated, but it will take up more time than I want to. So there is a way of lower bounding size by means of just lower bounding width. There is this notion of the length of a refutation. So that's just how many clauses appear in the refutation. And for resolution, this is very closely tied to size because a clause basically has length. Well, it contains just n symbol, or it was 2 n symbols, just if you add the negations, or n is the number of variables. So the size of a refutation is obviously lower bounded by the length. You know, if there are 7 clauses and the size is at least 7. But then again, if there are 7 clauses in the proof and the number of variables is n, then basically the size of the refutation is 7 times n or something like that. So for resolution specifically, this is a thing that's pretty unique to this proof system. Size meaning, you know, the total size of the proof in terms of number of symbols, and the length meaning the number of steps in the proof, number of lines in it, is more or less the same thing, or they're easily bounded in terms of one another. So, well, LR of F will be the minimal rank of a refutation of F. And there is this pretty famous paper of Eli Ben-Sasson and Avi Wigderson called Short Proofs Are Narrow or Small Proofs Are Narrow. I always get confused. It's one of the two. I think it's Short Proofs Are Narrow. That gives a lower bound on the length in terms of proof, a lower bound on the width. So the basic result, this is already corollary, a reformulation of their basic bound. Their basic result is that if you have a short proof, then there is going to be a possibly different proof that has low width. typically it might not be short anymore, but it will be low width. So if you can prove lower bounds on the width, then you can prove lower bounds on the length and therefore the size. And the lower bound actually is as follows. So length is exponential in something linear in a fraction where the denominator is the number of variables and the numerator is square of the following expression. You take the width lower bound and you subtract from it how wide the clauses of f are. So if k is f is a kc and f you subtract k. Okay. So just let's look at the specific. As I said, we won't claim this as our size lower bound because we're not going to prove Benson-Wigderson, but what would happen if we applied it to our bitwise PHP formula? So it has m times log n variables. So for instance, if n is n plus 1, this is basically n times log n. And the clauses have width logarithmic. Well, twice logarithmic, but never mind the 2, okay? So if we plug it into this formula, we get a lower bound of n on the width. So this is an n minus log n, so that doesn't really matter. This is basically n squared in the numerator. And here it's basically n log n. So n squared divided by n log n is n over log n. Okay, so the lower bound we get, yeah, there should be some sort of 1/2 or something like this in the exponent here, but never mind. We basically proved a lower bound of 2 to the n log n on the size or the length of the refutation of our bitwise Pigeonhole principle in resolution. Now, we want something that we can actually do by hand within the remaining time. I guess I'll give the strategy of the proof right now, and we'll discuss the technical issue if there is any. It's not really particularly difficult in class. Let's use another complication of the formula. Let's introduce something called relativization. In logic, there is this idea of relativizing a formula or relativizing quantifiers. So here we have a structure, say a first order structure, some sort of model. You can, if you don't know any first order logic, you can ignore this short discussion. I want to make it so you can see that where the inspiration comes from. The structure has some predicates, so the predicate picks out some of the elements of the structure. So you may want to talk about the structure restricted to, or the substructure with universe restricted just to this predicate. So to talk about it, you can do it by relativizing quantifiers. So instead of saying, if you want to know if the substructure given by U satisfies some formula, you replace each for all x quantifier in the formula by for all x if U of x then blah blah blah, and you replace exists x by exists x such as U of x and blah blah blah. That's relativization. So we do something like that, but on a propositional level. Let's look at the relativized bitwise PHP with two different parameters, M1 and M2, and still the same number of holes, N. So in general, M2 is going to be the number of all pigeons. It's going to be the larger of the two M's. And M1 is the number of, say, active pigeons, the number of pigeons that are going to fly, so to speak, that we need to find a hole for. And this principle says, still in the same bitwise fashion, that each of these M1 pigeons that fly, of the active pigeon, finds a hole and it's found in an injective way, and we don't care about the pigeons that don't fly. So our variables are xij for I, the index of a pigeon, any pigeon, not necessarily active, and j, a bit index for a whole number. And uki, where k is now smaller than the smaller of the two m indices. It's smaller than the number of active pigeons, and I is the index of a pigeon. So the idea is that, well, xyij means the same thing as previously. Uki means that pigeon number I is the kth active pigeon. Okay, so among the active pigeons, the kth one is pigeon number I. And the clauses are as follows. Firstly, for each k, there is a kth active pigeon. So, for each number of an active pigeon, there is this numberth active pigeon. Okay, M1 is a smaller number, it's the number of active pigeons. And it has to be one of the actual pigeons from 1 to M2. Secondly, it's not the case. So the map from indices of active pigeons to pigeons, it's actually injective. So it's not the case that the second active pigeon is pigeon number 5, and then the 10th active pigeon is pigeon number 5 again. We don't want that to happen. And finally, if you've got 2 active pigeons, if say the ith pigeon is active and the I prime pigeon is active, then they don't go to the same. So it's more or less the exact same thing, but relativized to active pigeons. So now we can prove a size lower bound on this thing, where the number of holes will be n. The number of all pigeons will be 2n, so that's double the number of holes, and the number of active pigeons will be n plus 1, minimal possible. Okay. So the details will, I guess, be relegated to class, but I want to discuss the full strategy and what we're going to do, and then we'll just discuss how you count some things or whatever in class for 5 to 10 minutes. We'll see. So we're going to use a technique known as random restrictions. So we're going to choose at random a partial assignment to some of the variables. So let's discuss. Restriction is simply a partial assignment. You set some of the variables to 0 or 1. So given a clause and such a partial assignment, such a restriction, rho, the clause C restricted by rho is defined to be the following. If rho makes one of the literals in the clause true, then C restricted to rho is simply true. It's a true clause. We no longer care about it, in fact, because it's not helpful in refutation anyway. If there is no such thing, so if no literal in C is satisfied by rho, then we throw out the ones that are falsified. They're not going to contribute to making C true. So let's look at an example, and let's look at what such a rho does, not just on a clause, but on a refutation. So assume that you had a refutation here. Assume that you had a refutation here, where one step was the following. You knew that X or Y, you knew that not X or Z, and you derived your resolution Y or Z, right? The typical use of resolution. So let's apply the restriction that sends X to 1, to true. What happens to each of these clauses? This one becomes what? Shimon, I was supposed to ask simple questions to the audience throughout the lecture, so I may start now, right? So what happens to this clause? X or Y?
It becomes true.
It becomes true. So it's going to be constant true. It won't play any role in the refutation. We'll basically erase it. What does this clause become?
Z.
It becomes exactly Z, right? And this is still Y or Z. So this piece of the refutation becomes the following thing. From Z, derive Y or Z. So this is not strictly the resolution rule. This is the rule we know as weakening. So take a disjunction of literals and add some new disjuncts. So what happens to a resolution refutation is that it still remains a resolution refutation, except that maybe now some parts of the refutation terminate in just or become populated by tautological clauses. We simply ignore them. So the refutation might only become smaller. The number of clauses in the refutation does not increase. Surely the width of the clauses doesn't increase either. It might decrease. But now we have these weakening inferences. Weakening is totally harmless in resolution. It doesn't change any width or size lower bounds, so we can actually add it to the system. So a refutation restricted by rho is still a refutation. Now, let's look at what a particular restriction does to our formula. So can I take 5 more minutes, or will that be very bad? I'll take 5 more minutes now to finish up this story, and we'll do a computation during class. So let's consider the following distribution of probability distribution restrictions. We will choose uniformly at random an injection from n+1, that's the number of active pigeons we're supposed to have, to n, that's the number of all pigeons that we have. So if in this injection k gets mapped to I, then we say that the pigeon number I is the kth active pigeon. We set UKI to 1, and we set all UKI for those k that don't get mapped to I to 0. So we completely determine the value of the U variables. This injective tells us which pigeons are active pigeons and which number of active pigeons they are. This won't really matter anymore. And all the all the rest, all the other variables, U variables are set to 0. And now for those pigeons that were not selected to be active, we flip a coin to set the variable, like independently for each xij for an inactive pigeon I, we flip a coin to decide the value of the variable xij. Okay, so we do it completely at random because we no longer care about them. They're inactive, so their connection to the holes is totally irrelevant. And we leave all the rest unassigned. So let's look at what happens to this relativized bitwise pigeonhole principle with these parameters under a restriction row. Under this form of restriction row, what happens? Let's go back to the clauses of this relativized PHP. So firstly, each of these guys simply becomes true. It's irrelevant. Each of these guys also becomes true. Okay, because this map taking k to i's is simply that's a row, that's an injection. And for these guys, there are two possibilities. Either both of these pigeons are active, in which case this is a 0, this is a 0, and we simply get the original clause of bitwise PHP. Or one of them is inactive, in which case one of these guys is a 1, so the clause is tautological, it's constant true. In other words, what remains after doing such a restriction, whichever one from our distribution, is simply the original bitwise PHP, but just indexed not by pigeons 1 through n+1, but by the n+1 active pigeons. So this the CNF that we are refuting is, after this restriction, is isomorphic in a natural sense by re-indexing the variables to our bitwise PHP of n+1 and n. And then the question is, what happens to a not too large refutation of relativized bit PHP under such a restriction? And what we'll check in class is that it becomes a restriction of small pigeon width, in the sense that each clause doesn't mention too many pigeons with non-zero probability. So there is a restriction that turns a not too large refutation into a low pigeon width refutation. And that's something that we can already rule out. So that will complete our argument. Okay. So that will be our size lower bound for relativized bit PHP. To complete the story for today, let me say the following. Let me do a very quick survey of how the pigeonhole principle behaves in general in proof systems. So essentially, any reasonable form of the pigeonhole principle is hard for resolution. Proofs of this may become much harder for difficult choices of parameters, but I don't really know interesting examples of PHP that are provable in small size and resolution. Essentially, everything is easy for Fraga systems, for these textbook systems, because it's actually non-trivial, but they're able to count. So you can use small formulas. They have to have large depth, but they can be kind of small to simulate counting and therefore disprove PHP. Most forms of PHP remain hard for polynomial calculus with resolution, but there are particular ones that aren't hard anymore. So for instance, if we strengthened PHP to say, not only is the map from from n plus 1 to n, an injection. It's not just an injective multifunction, but firstly it's a function, so it's an actual injection, and it's actually surjective as well. So you can write down a CLF that says there's a bijection between exactly n plus 1 and n. And here it matters that it's n plus 1. It's not just greater than n, but it's exactly n plus 1. And polynomial calculus can refute that. It can basically sum up all the holes on the one hand and all the pigeons on the other hand, and it will get 1 equals 0. Maybe we'll do that on Saturday in class if there's time. I don't know, or maybe I'll leave it for you as one of the exercises. That's something that is reasonably difficult. Then there's this major result from the early 90s that any variant of the PHP, the bijective variant of strong PHP, so injection of n plus 1 pigeon to n pigeons, that's exponentially hard for these bounded depth systems that I mentioned. But on the other hand, if you take the weak PHP, so you only have to rule out an injection from double the number of holes into the number of holes, then ruling out such a thing can be done in a bounded depth system. In fact, just a bit over resolution, perhaps not in polynomial size, but in quasi-polynomial size. And there's a major open problem here that, I mean, solving it would be pretty important, I think. Whether you can actually show that there is no injection from between 2 n pigeons and n holes, or even between n squared pigeons and n holes, whether you can prove that by a bounded depth proof in polynomial size as opposed to quasi-polynomial size. And this is one of these problems that have been open since mid-80s, I guess. And maybe there's been a little bit of progress, but nothing essential has changed. Okay, so I guess I stop for today in terms of the lecture, and we resume at 1:15, unless we should extend the break. That's your call.